First speaker this morning is Olga Varghese from Universität of Münster, who will tell us about the profinite properties of Dyer groups.
Yeah, thank you very much. So thank you very much for having me here. Today I want to talk about profinite properties of Dyer groups. So first of all, I want to introduce you to Dyer groups. So let me start with the definition. So let gamma, M, and F be a triple consisting of a finite simplicial graph gamma and so M is an H labeling. So each H has a label which is greater or equal to, and F is a vertex labeling. So each vertex has a label, a finite label, which is greater or equal to, or infinity. And we call this triple a Dyer graph. If the following holds. So given an H, E with vertices V and W, with H label greater than 2, then the vertices V and W have label equal to 2. Then we can associate a group to this graph, the Dyer group. So the Dyer group which is associated to this graph is given by the following presentation. So the generating set of the gamma is the set of the vertices of gamma. Then for each vertex, we have the following relation, V to the power of the vertex label, whenever the vertex label is not equal to infinity. And for every H, we have also a relation, VW, VW, and so on is equal to WV and WV, and so on. Here and here we have M, VW letters. So whenever we have finite graph with a nice H labeling and a nice vertex labeling, then we can associate a group to this graph. a Dyer group. So Dyer groups first appeared in a work by Dyer in 1990. And so let's do some examples. Because I think that this definition of a Dyer group looks very familiar. So for example, if gamma is a triangle where each vertex has label 2 and every edge has label 3, then the associated Dyer group, D gamma, is a Coxeter group of type A22, which has a very nice algebraic structure. So this group is isomorphic to a semi-direct product of Z2 and Z3. So more examples. If every vertex in the Dyer graph has label 2, then the associated Dyer group is a Coxeter group. And if every vertex has label infinity, then the associated Dyer group is a right-angled arting group. So the family of Dyer groups contains all Coxeter groups and all right-angled arting groups and also all graph products of cyclic groups. And this gives us a very nice framework to study these groups in a unified way.
Don't you allow infinite labels of edges?
Edges, no.
But then why does it cover all Coxeter groups?
There's no edge.
Oh, there's no edge.
Yeah. Then we have. So given a Coxeter group, there are always two graphs which are associated to this group. So we have this Dinkin diagram graph, and there's this model notion of Coxeter graph, and the way you like. Okay, so today I want to focus on profinite properties of Dyer groups. Therefore, I'm going to denote by F, G, R, F, the class of all finitely generated residually finite groups. So given a subclass of this class of groups, so given C, a subclass of all finitely generated residually finite groups, we say that a group G in that class C is C profinitely rigid if whenever we have another group in this class with isomorphic profinite completion, then G is isomorphic to H. So if this holds for all H and C. So, and as usual, if C is equal to FGRF, then we say that G is profinitely rigid in the absolute sense, or for short, G is profinitely rigid. And I think the canonical question now is goes as follows. Are Dyer groups d-profinitely rigid? Where D is a class of all Dyer groups. So this question has particular relevance to broadly studied but unsolved isomorphism problem for Coxeter groups. And it was observed by Bryson, Conder, and Reed, and also by Gardam, that whenever one has a class C of finitely presented residually finite C profinitely rigid groups, one obtains a solution to the isomorphism problem. And that class of groups, so we have this very nice fact. If Dyer groups are d-profinitely rigid, then the isomorphism problem for Dyer groups is solvable. So it's not so obvious, but one can show that all Dyer groups are linear groups, and therefore they are residually finite. But it's not so obvious.
It's something like the Coxeter representation.
So one can show that given a Dyer group, d gamma, then there exists a Coxeter group, W omega, such that we can embed d gamma in W omega. Okay. Okay, so back to the question. So are Dyer groups d-profinitely rigid? So we do not know the answer to this question, but we have some results. So some examples. So it was proven by Kropholler and Wilkes that right-angled arting groups are profinitely rigid amongst themselves. So by RAAG, I'm going to denote the class of all right-angled arting groups. So recs are rec profinitely rigid. And it is not hard to see that these groups are also d-profinitely rigid. So the abilinization is a profinite property in the absolute sense, and using this fact, I can show that these groups are actually d-profinitely rigid. So, next result. So what about graph products of finite cyclic groups? Because these groups are also Dyer groups. So graph products of finite cyclic groups. Are profinitely rigid relative to themselves. This was proven by us, so by Samuel, Carsten, Sam, which is in the audience, Philip, me, and 23. And again, it is not hard to see that these groups are d-profinitely rigid. Okay, so what about virtually abelian Coxeter groups? So what about affine Coxeter groups? So affine Coxeter groups are profinitely rigid in the absolute sense. Therefore, they are d-profinitely rigid. This was proven by us. Again, Samuel, Sam, Philip, in 24, and also independently by Paolini and Sklinos. 24. Okay, more examples. So what about small Dyer groups? And by small, I mean that the vertex set of the defining graph is not too big. So by definition, a Coxeter group W, so a Coxeter group W is called a triangle group. If W is isomorphic to a Dyer group which has a triangle as a defining graph. So here you can write D or W, whatever you like. I think that all triangle Coxeter groups should be profinitely rigid in the absolute sense. But so far we do not know. But there are some very nice results. So it was proven by Brightson, McReynolds, Spittler, and Reed in 21 that the following 14 hyperbolic triangle groups are profinitely rigid. I do not want to write all of them down, but maybe a couple. So here we have more. So 40. hyperbolic ones. So what do we know about the profinite rigidity of triangle Coxeter groups? So it is possible to show that all triangle Coxeter groups are de-profinitely rigid. So together with Sam and Philip, we proved this result for W profinite rigidity, and again, using the fact that the abelianization is a profinite property, one can extend this result to D profinite rigidity. So maybe one more result. So this list is not a complete one. So let D gamma be a virtually free Dyer group. So here we need the assumption that the Dyer group is virtually free. So if the vertex set of gamma is small, by small I mean the cardinality is less or equal to 4, then we can show that the corresponding Dyer group is de-profinitely rigid. So this is an ongoing work with Philip or maybe some other people, I don't know. Let's see. Okay. So many properties of Coxeter groups and also graph products of cyclic groups and therefore also of Dyer groups can be decided by analyzing the combinatorial structure of the defining graph gamma. And many of these properties are also de-profinite invariants. And because we want to prove profinite rigidity for virtually free Dyer groups, we need a combinatorial characterization of virtually free Dyer groups. So it goes as follows. So we start with a Dyer graph. So let gamma, M, and F be a Dyer graph. Then the corresponding Dyer group is virtually free if and only if the following 4 conditions hold. So here's the first condition. So if we have 2 vertices, V and W, with infinite labels, then VW is not an edge. So this is a kind of a trivial condition, because if there is an edge, then Z times Z is a subgroup of D gamma, and this is not possible because the group is virtually free. So if we have this then W is not an edge. Then the second condition, if we have a vertex with U with an infinite label, and we have two vertices, V and W, with finite labels, and so here we have U with infinite label, then we have V with finite label, and W also with finite label. Whenever we have here an edge and here an edge, then VW should be also an edge. Then the graph gamma is caudal. So there are no full cycles of length greater or equal to 4. And the last condition is that clique parabolic subgroups are finite or virtually cyclic. And the proof idea, just want to say one word. So the proof is very easy. Just by using Basset theory, it's actually very easy to show this result. So are there questions so far?
Examples you gave, are there any Dyer groups that are known to not be absolutely profoundly rigid?
Yes, so Dyer groups in general are not profoundly rigid. For example, F2 times F2 is not profoundly rigid in the absolute sense. So it's not profoundly rigid in the absolute sense. And for example, also, I don't know, so you can put here the universal Coxeter groups with greater or equal 3 vertices, something like Z2, Z2 times so this is also a Dyer group, this Coxeter group, so this right-angled Coxeter group is not profoundly rigid in the absolute sense. But we believe that all Dyer groups should be de-profoundly rigid. So this was proven by us. Oh, yeah. Yeah, not really. So here we need one more factor than proven by us.
Yes, that they are irreducibles, not all discounted.
Yeah, it's not known. Are there other questions?
So this virtually free theorem
No. So we have this very nice characterization of virtually free Coxeter groups, right? So a Coxeter group is virtually free if and only if the defining graph is caudal and every clique parabolic subgroup is finite. And we do not use this fact. We just can prove with Basset theory the whole theorem for Dyer groups. So this is a kind of a unified proof for all Dyer groups. But the proof structure is more or less the same as for Coxeter groups.
So maybe it works without the assumption that MP is different from Q, or do you use that? Because that's a crucial assumption.
Yeah, because we need the fact that intersection of parabolic subgroups in a Dyer group are again Dyer groups, stuff like that. And if we do not have this assumption, then all arting groups will be also Dyer groups, and this big conjecture if the intersection of parabolic subgroups.
Yes.
So other questions? Okay, then I want to sketch the proof idea to 5. So where's 5? Ah, here. That triangle Coxeter groups are deprofinitely rigid. Idea to 5 is 5. So let gamma be a triangle. Be a triangle. All vertices have label 2, and we have here labeled P, Q, and R. Then there are 3 possibilities for the associated Coxeter group or Dyer group. So if this sum is equal to 1, then the associated Coxeter group or Dyer group is affine. And then we already know that here by the result in 3, that affine groups are profinitely rigid in the absolute sense, therefore they are also deprofinitely rigid. If this sum is greater than 1, then W gamma is finite and there's nothing to prove. And if this sum is less than 1, then the associated Coxeter group is Gromov hyperbolic. So we assume that this sum is less than 1. So we are in the hyperbolic case. So let W omega be a Dyer group with isomorphic profinite completion as W gamma. So our goal is to show that the omega is isomorphic to W gamma. So first, using the fact that the abelianization is a profinite property, we can conclude that the omega is also a Coxeter group. Okay, this is the first step. So then, so hyperbolicity is in general not a profinite invariant in the absolute sense, but if we restrict the class of finitely generalized residual finite groups to Coxeter groups, then hyperbolicity is a D profinite invariant, or is a W profinite invariant. So, Rom of hyperbolicity is, and by W I mean the class of all Coxeter groups. Finite invariant. So we know that the omega is hyperbolic. Okay. Okay, so we have a very nice characterization in terms of graphs of virtually surface Coxeter groups. So in particular, W gamma is a virtually surface group. And this property is a profinite invariant amongst all hyperbolic Coxeter groups. Therefore, so using the fact that virtually surface, so being a virtually surface group is a profinite invariant amongst hyperbolic Coxeter groups. We know that the omega is a virtually surface group. So, and again, using the characterization, a combinatorial characterization of virtually surface Coxeter group, we know that the omega is a direct product of a finite Coxeter group, which corresponds to a full subgraphs of omega, and a cycle, and this cycle is, we do not know the length of the cycle, but we know that this cycle is a full subgraph of omega. And here we have, I don't know, x1, x2, x3, x4, xn. Okay. Then, okay, here we have something finite, right? In W omega does not have non-trivial finite normal subgroups. And having non-trivial finite normal subgroups is also a profinite invariant amongst hyperbolic groups. Therefore, so non-trivial subgroups. So having non-trivial finite normal subgroups is a profinite invariant amongst hyperbolic Coxeter groups. W omega does not have non-trivial finite normal subgroups. Therefore, W gamma does not have non-trivial finite normal subgroup. Therefore, the omega does not have non-trivial finite normal subgroup. Therefore, we know that this group is trivial. So, omega is a cycle. Okay, this is nice. So we need more profinite invariants to deduce that omega is actually a triangle. So we need one more trick. Okay, so we denote by CF. So for a group G, we denote by CF max of G the set of conjugacy classes of maximal finite subgroups of G. So conjugacy classes of okay. So for example, CF max of W gamma consists of 3 elements. So we have here the conjugacy class of the parabolic subgroup which correspond to the HP. Here by this I mean just, so this is the conjugacy class of the group which is generated by PW. And here we have U and R. So W gamma has exactly 3 conjugacy classes of maximal finite subgroups of G. So each H corresponds to the conjugacy class of a maximal finite subgroup. And the same holds for the omega. So here we have x1, here we have xn. So each H again corresponds to the conjugacy class of a maximal finite subgroup of the omega. And one can show that CF max is a profinite invariant amongst all virtually surface Coxeter groups. Profinite invariant. So we know that this set has also exactly 3 elements. And we also know that the multiset PQR is equal to x1, x2, and x3 as multisets. So actually we do not know if CF max is a W profinite invariant. But if we restrict the class of Coxeter groups to virtually surface groups, then this is the case. So, using all this very nice profinite invariants, we conclude that omega is a triangle, because we have here only 3 edges, so each edge corresponds to a maximal finite subgroup, and we know that the multisets are equal. Therefore, we know that omega is equal to a triangle with labels P equal R. So, and then this is trivial. Gamma is isomorphic to the omega. So, other questions? Okay, so triangle Coxeter groups are nice, right? So we can actually, so using a bunch of different profinite invariants, we can show that triangle Coxeter groups are deprofinitely rigid. So what about cycles of bigger lengths? And actually we do not know. For example, if we have a cycle with length 4, so there should, I don't know where, here. So for example, if gamma looks like as follows, so if gamma is a cycle of length 4, so again, a Coxeter group. And so I like prime numbers, so I'm going to put here primes, so 3, 7, and 11. Then we do not know if the corresponding Coxeter group is W profinite rigid or not. So we can show that, so assume that W omega is another Coxeter group with isomorphic profinite completion, then using the same tricks as here, we can actually show that omega is a cycle of length 4 and we can also show that the multisets should be equal, or the sets is equal but we do not know if the edge, here we have an edge with label 3 is connected to the edge with label 5. And here we do not know how to recognize this condition. So this is open.
I'd like to make a comment on this. These groups can be distinguished. It is an ongoing work by me and Tan Cheatham West.
Oh, nice.
Yeah. I'll tell you a simple idea about this. Because like these groups are conjugacy separable.
Yeah.
You can know that the elements in CF max, whether they have conjugacy representatives that intersects non-trivially or not.
Okay, I see.
So in this case, the dihedral groups corresponding to 3 and 5 have non-trivial intersection.
Yeah.
And so they have non-trivial intersection if and only if they have a common vertex.
Oh, nice.
So you know when two of these edges
Yeah.
are joined together by a common vertex, so you know the cyclic order.
Oh, perfect. So you can do it for cycles of length n, right?
Yeah, any length.
Any length. Oh, nice. Nice to hear, Sam, right?
Sorry?
Nice to hear, it's Sam, right?
What was the question?
That gamma and omega can be distinguished by the ongoing work of you and some other guy.
I think Martin wanted to.
Oh, okay.
It was the same proof.
Yeah, nice to hear. So, okay, perfect. Then we have a new result which we can add to the list here. Okay, so I have 8 minutes left, and I want to sketch a proof idea to the fact that right-angled Coxeter groups are d-profinitely rigid. So, the 2. So 2 was about graph products of finite cycle groups. Here I want to sketch the idea that right-angled Coxeter groups are W or d-profinitely rigid. So, so this set CF max of G is a very nice set. So we can also consider CF of G. So given a group G, then we can denote by CFG the set of conjugacy classes of all finite subgroups of G. All finite subgroups. Then I can show the following very nice fact about right-angled Coxeter groups. So given 2 right-angled Coxeter groups, W gamma and W omega, then the following conditions are equivalent. Then CF of, so I forgot something, but okay, W gamma is isomorphic to or equal to CF of W omega if and only if the groups are isomorphic. So this is true for right-angled Coxeter group, and here we need an order isomorphism. So this set CFG is a poset with the following order. So it says that A is lesser or equal B if and only if there exists G in G such that A is contained in a conjugate of B. So, and given 2 right-angled Coxeter groups, then the groups are isomorphic if and only if we have an order isomorphism from CF W gamma to CF W omega. And in general, this is not true want to give an example. So, for example, the Coxeter group, which is associated to the following Coxeter graph, 4, is not isomorphic to the Coxeter group, which has the following Coxeter graph. For example, I don't know. So the group which is associated to this graph is W1, and this is W2. Then one can show that CF of W1 is isomorphic to CF of W2, but W1 is not isomorphic to W2. Now, because, for example, this group has CS property of A, but this group does not have FA. So we have this very nice statement, but this statement only holds for right-angled Coxeter groups and maybe other Coxeter groups, but this statement does not hold in general. Okay. So, I want to show you the proof idea that right-angled Coxeter groups are deprofinitely rigid. So let's start with a right-angled Coxeter group. So let W gamma be a right-angled Coxeter group, and D omega be a Dyer group. Then Dyer group such that the profinite completion of W gamma is isomorphic to the profinite completion of D omega. Then again, using the abelianization, I can show that D omega is a Coxeter group. Then the canonical map from W gamma to the profinite completion of W gamma induces an order isomorphism from CF from W gamma to CF, and here we have the profinite completion. So this fact can be shown using the profinite Vasseur theory. So using this fact, one can show that D omega should be a Coxeter group, because otherwise the profinite completion of D omega would have finite order elements not equal to 2. Is the rec. And then using this very nice CF stuff, so CF, so this set is a profinite invariant amongst all right-angled Coxeter groups using this, where I can show that CF of W gamma is order isomorphic to CF of D omega. And then we know that W gamma is isomorphic to D omega. Okay, and this is all what I wanted to say. Minus 7 seconds. Okay.
Are there any questions?
About your example of W1 and W2. So what happens? So just looking at it, it looks like there's different. What happens? Why do they have the same number of maximal finite?
Okay, so maximal. So here we consider all conjugacy classes of finite number subgroup, but if we restrict to max, then here we have four. Here we have three, right?
Yeah, that's right. So why get
And here we have this one, and this one. Here we have also three maximal.
Oh, that's fine.
Yeah.
Nice.
And then one can actually show that CF of W1 is whatever. Yeah. Otherwise, we could maybe do the same stuff as here.
So the idea is that you just have attach a finite triangle group to your. You can kind of this example kind of you can keep doing this. You keep kind of attaching finite triangle groups to kind of keep the maximal groups.
I think so. So so I think it is a very nice question. So maybe it is possible, I don't know, to characterize all Coxeter groups such that this result holds. And yeah, I don't know if this is the only strategy to obtain this kind of stuff, putting here triangles. But maybe there's something else.
No other questions? Okay, then let's thank Olga once again.